So these look pretty good. Can you put your board right side up, please? And then just put it on your lap so everyone can see it. Thank you. All right, tell me about the boards, please. When you look at them, what do you notice?
They're all linear.
Are they all linear?
Yeah.
Okay. What else?
Everybody has a table of data.
Well, we're not talking about surface features. Okay. We have units on the slopes?
Yeah.
Okay. Do we all have similar units? What are your units?
Second squared over
meters.
Your units are newtons times second squared over meters. Okay, where on earth did that come from?
So you have to do y over x, so you would get n times s over m over s, and then you would take the reciprocal and you would end up getting
What was that?
ns squared over n.
So let's start with some basic understandings here. Like, what are the units? Okay. No, the units for your each. Sophia, tell us about your units.
Area is n times s and velocity is meters per second.
So the change in velocity of units meters per second. And for this force time area, what are the units?
N times s.
So it's Newton seconds. Now you didn't label yours, Sophia. Okay.
On the graph.
All right. So we got newtons times seconds. That's a weird unit, right? Because oftentimes we don't have. We normally divide things. It's not oftentimes we multiply these together, but it's Newton seconds. Okay, and then so then you just did kind of like a vertical divided by horizontal, and then you tried to simplify. Okay, does that make any conceptual sense? Like if I said, oh, your units are newtons times seconds squared divided by meters, does that help you understand it all?
Yeah.
No, I have no idea.
Why not?
I don't. Does it?
It helped me. Okay, well you took it.
Well, in what way?
It helped me understand the slope. Wait, what are you asking? If it helped, no, what are you asking?
If I gave you a number, I said, oh, the number's 4, newtons squared divided by meters, would that give you an indication as to what quantity we're talking about?
No.
I don't think so either. Okay? If I said, oh, your number's 4 meters per second, would you know what kind of quantity we were talking about? Yeah, right? That'd be meters per second would be a speed. Or if I said, oh, your quantity is 4 newtons, would you know what that was? Right? You with me on that? I don't think the way the units are helps us understand more deeply. We'll come back to it. Tell me more about the whiteboards. So you can tell me something that you notice is the same or something that you notice is different.
Somebody has linear graphs.
Okay, linear. I like it. What's that?
Oh, we already said that.
This,
That's fine.
Like coefficient, this number is kind of similar for most of them. We have the same as they do. And,
Your slope is the same?
slope is
Pretty similar.
Are they?
Kind of.
Okay, let's talk about them. What's your slope?
0.62.
So your slope number is 0.62?
0.5.
0.62, 0.7. 0.47, 0.48. You guys 0.62.
We're 0.55.
0.55, and Brendan, what is your slope?
0.567.
So I actually feel like these are all very close, to be honest with you. Maybe within experimental error. Does the slope have any actual physical significance?
like how much the area changes for like one
Depending on the
velocity.
speed.
Yeah.
So if you had like a change of 1 meter per second, okay, would that give you an indication as to how much force time area you had?
How much what?
The force time area. See, the thing about this is that
What?
the thing that I find actually very challenging about this lab What's going on over there? The thing that I find hard about this lab is that we're not just taking just one measurement off a graph. So this is the time, this was the force. You guys were looking at like the area of this graph as one of your measurements, right? And so we're going to measure this here. We can say, oh, well, here's my force time measurement. Now, if the maximum amount of force were larger, but it had the same area, you would get a larger time, you could get a larger force time area. For example, what if I did this? So the time component is the same, but the maximum force is larger. So what do you notice about the total area here then?
Larger.
Okay? What happened there? So we have to take into consideration both how much force is applied and how long that force lasts. This is kind of a new framework for us to consider two things at the same time. So if I go back, okay, let me do a little purple one here. I'm going to let the purple one have more force, but it lasts for less time. If I do the area of this purple one, is it possible that the area of the purple one and the area of the red one are the same?
Yeah.
Is that a possibility? One has more force but less time, right? What if I did even a third one? What about this one here? It has less overall force, but that force lasts for more time. Is it possible that all three of those colors have the same area?
Yeah.
Right? It might be. Now, it's also within my ability to draw it. So what are the units for the force time area?
Newton times seconds.
The units are just
Newton
seconds. What we do is we can visualize this like, well, what if it were a rectangle? We would do base times height,
I can drive on.
okay? If it was base times height, we'd have seconds times newtons. Does that make sense?
No
Okay.
such thing. I told you there's not thing.
All right. So what kind of relationship are we seeing then? What kind of relationship is this? Linear? Is it linear? Is it proportional also?
Yes.
It is or it's not?
I think so.
What would lead you to believe it were proportional?
It's like it increases the same amount each time.
Okay. So we have a constant linear. Tell me about the intercept.
Negative 0.002.
All right.
That's around 0.
Is it around 0?
Yeah.
Is it 0 enough?
Yep.
Okay. Conceptually, does it make sense that it should be 0?
Yeah.
Check with your neighbor. What about the concept makes it in your head say like, yeah, 0 makes sense to me. Go ahead and check your neighbor real quick. See what your neighbor says.
No change in I didn't know that you were talking.
It's happened.
Oh my God. You guys.
We don't grab it.
Anyway,
Like I'm crazy right now. But I'm acting.
all right. Ren,
What?
does it make sense to you that the intercept should be 0? Tell me why.
I don't. Next question.
Listen, really though, if I say check your neighbor, make sure you do that because I'm not trying to like catch anybody or embarrass anybody. I just want you to have an answer when it comes to you. Does that make some sense?
Yeah.
All right. Kaylin,
Yeah,
does it make sense the intercept should be 0?
yeah, because if velocity is 0, then like you can't have an area.
So what's on that horizontal axis? It's not the velocity. What is it? It's the change in velocity, true? Okay. So if your change in velocity is 0, what did that mean about your object? That's true. Joe said something interesting. She's like, well, if there's no change in velocity, then it's not accelerating. But that also means that there's no unbalanced force on it.
Okay, I have something to say. Well, you don't have to change it.
Go ahead.
Okay. So in the lab, what caused the change in speed was the force.
Yes.
Like by hitting the force, that's what caused the change in the speed. So if there's no force, then there's going to be, or there's no force time area, then there's going to be no change in speed.
Yes.
So that's why it makes sense to me.
Okay.
That's what I'm answering your question. Wasn't that your question?
That's great. That's a great thing.
Okay.
Okay, you guys okay with that? So according to what you have, okay, according to what you have, and I'm going to summarize it on the board here, and then we're going to do the next part of the activity. Okay. According to what you have, you're saying that if you have an object, okay, focus please. If you have an object and you want to change its velocity, okay, you need to apply a force, and that force needs to last for some period of time. Okay? So visualize your object. You have an object. You want to change its velocity. You need to apply a force, and that force needs to last for some time. Is that cool? Yeah. And it makes sense that if you want a larger change in velocity, what can you do? You can apply more force, or you can make that, that's right, you can make that force last for more time, because it's the area, as we saw in your lab, it's the area that determines the change in velocity. Is that cool? All right, now, you told me here a moment ago that the units for this were Newton seconds divided by meters per second. Is that true? Now, you did a great thing. You somehow simplified this to newtons squared per meter. Is that true? Mm-hmm. All right. I'm going to remind you of something, and then we're going to do a little bit more work. So you're going to need a whiteboard marker for this. But here's the deal.
Oh my God, not again.
If you remember,
If you get that marker out, I'm going to lose it.
okay, focus please, I don't want you to miss this. If we go with the law that you guys developed earlier this year that says the acceleration is the ratio of the force to the mass. Do you remember that? Does it seem vaguely familiar to you? If you rearrange this mathematically, you end up with force is equal to mass times acceleration. Is that cool? Now, if I work the units on this, the units of force are newtons, and the units of mass are kilograms, and the units of acceleration are meters per second. It's per second, but we can call it meters per second squared. So what I want you guys to do on your whiteboard now is to make a direct algebraic substitution. Take this Newton here, substitute it into this thing, and simplify, and see if we can't come up with the actual, conceptual units for acceleration.
I'm not
You
using
ready?
that marker.
Here, I'll just take that marker.
Yeah, thank you.
No,
Thank you.
We don't need to deal with the drama. All right, are you? Do it right on your whiteboard, please. Do it right on your whiteboard, please.
You should have.
Simplify that. Substitute that, and we're going to rewrite as kilograms times meters over second squared. And see if we can simplify that down into something. We're going to make a direct algebraic substitution.
So it's literally
And
just
then-
algebraic circles.
Right, so what we do is times.
For the,
So the S would just cross out. And
Yeah.
then, yeah. So that-
Plug in the newtons, right? Kilograms?
So the word. Is that just for the
so
it's
it's,
just
this marker is not there.
Just throw it out.
Yeah, the one you grabbed
Is it just
Okay, so
kilograms?
I was simplifying that.
Isn't your like up there?
is this right? And then over.
What?
So this is the S mark. So those cross it. Oh, wait, I forgot. I can't read it like that.
See, Brendan, I was.
I never said you weren't right. I literally said, that's right.
I wouldn't say. Oh, we wrote
Yeah.
that. That's about to open it up.
What's your pattern, bro? What is this?